New pictures acquired by the James Webb Space Telescope have staggered specialists. Rather than expanding our viewpoint on the universe, these photographs revealed an upsetting reality. Our constant appreciation is deficient in making heads or tails of the possible consequences of the universe in its beginning stages, where the speculation of the Big Bang seems to reach its limits. This drives us to consider new theories regarding its beginnings. The question emerges: how is the universe formed? And why does this new openness challenge even the most experienced specialists to understand more about the Big Bang and the complex details of the discovery? Shouldn't we examine the possibility of the Big Bang itself, disregarding standard reasoning? The Big Bang was not an effect in previous space. Perhaps it was space itself that began around 13.8 billion years ago alongside matter and time. An eccentricity in material science and cosmology describes points where gravity is so extreme that the curvature of spacetime becomes limitless. Today, following billions of years since the start of the universe, we see that our colossal home is part of a grand cycle. For specialists, this addresses a fundamental piece of the universe since its very existence. It's obviously a perpetual advancement. Anyway, it's crucial to understand that the universe isn't floating into past space. Rather, space itself is constantly expanding in size, as demonstrated by current hypothesis. The first stars began to shine somewhere between 200 to 300 million years after the Big Bang, marking the end of the so-called Dark Ages. This was when the first brilliant, wonderful objects combined to form mature systems. However, how quickly these boundless systems formed remains a baffling mystery. An abundance of data arose through the first pictures captured by the James Webb Space Telescope in July 2022. Specialists uncovered that the telescope had identified interesting galactic systems, some of which had already existed around 300 million years after the universe's formation. However, rather than the huge, permanent structures that formed much later, these early galaxies were significantly smaller and less massive. This aligns perfectly with the scientific model accepted by specialists. The density of matter in the early universe was simply not enough to create galaxies the size of those observed today. These observations began with the identification of 6 glowing redshifted spots from the James Webb Telescope. These findings triggered one of the most important cosmic mysteries in recent years. Although these newly discovered galaxies are similar in age to more recently recorded ones, they are generally as large as our own Milky Way. This has created an intriguing mystery. Later, upon examining a series of images captured by the near-infrared camera, specialists identified the previously mentioned light sources. Using redshift to confirm that the light from these objects took over 1 billion years to reach our eyes on Earth, it was concluded that the Webb telescope had captured 6 early galaxies in its photographs. Amazingly, these galaxies were so large that they challenged typical theories in cosmology. Rather than finding the usual smaller galaxies, structures were identified that were almost as vast as our own Milky Way, despite having formed early in the universe's history. If we continue to investigate the data collected by the James Webb Telescope, this gravitationally bound collection of stars was already more than 10 billion times the mass of the Sun at that time, with one perhaps surpassing 10 billion solar masses. However, whether this scenario is accepted remains uncertain. For instance, there would have been significantly more mass in the early universe than previously anticipated, which presents an issue. The identified objects challenge nearly all conventional cosmological theories. If even one of these immense galaxies turns out to be real, it would contradict our earlier assumptions. Moreover, the density of matter in the early universe would have to be several times denser than previously predicted to account for this anomaly. Another equally strange explanation depends on how these grandiose systems formed, something that remains completely unknown to us. These discoveries and the discussions surrounding the Big Bang have prompted some scientists to deviate from this theory. Other astrophysicists with alternative viewpoints feel their perspectives are not being heard in scientific journals. Indeed, even those who express doubts about existing theories are often labeled as ridiculous. However, it's clear that even specialists who still advocate for the Big Bang theory are continually faced with questions that require convincing answers. These inquiries include specific issues like why and how, 13.8 billion years ago, something arose from nothing. Might something truly ever begin from nothing? Or was there some triggering event? Or was it all just a coincidence? Steven Weinberg pointed out that the concept of time, as we understand it, began exclusively with the Big Bang. Thus, this process could not have been triggered by something beyond it. A similar perplexing question relates to the uniformity of radiation and density throughout the universe. No matter which direction we look, or at what distance on a larger scale, we find similar densities and distributions of galaxies, nebulae, and radiation. Normal researchers explain this phenomenon through the theory of inflation. However, some specialists take this assumption further with a theory of wild inflation. According to this idea, inflation has only stopped in specific regions, like bubbles, and continues infinitely elsewhere. This suggests that other universes could be forming in these bubbles, each with its own unique physical laws. In this model, a key question arises: what if our universe does not represent the entire picture? More intriguingly, what if another universe existed before our own? In this case, the Big Bang would become part of a larger cycle. According to this view, our universe is part of a greater multiverse. Within this framework, the possibility of an eternal cycle of death and rebirth of universes is advanced. However, this isn't the only perspective presented in the field of cosmology. In 1955, for example, an article appeared in NASA's Spacetimes arguing that there may have never been a Big Bang because the universe has existed for an infinite amount of time. In this view, the expansion of the universe would be non-existent, and the predicted structure of matter could give the appearance of constant development. Additionally, another fascinating hypothesis arises from the realm of quantum physics and string theory. Some tests have suggested that our universe and everything in it could simply be a flat, three-dimensional image projected onto a surface. Thus, there is a possible idea that our reality is the result of a higher-level simulation. While this might sound like the plot of an imaginative science fiction movie, it could possibly be linked to the Kardashev scale, which measures the level of advancement of a civilization based on its ability to harness energy. If there were a Type 3 civilization capable of fully utilizing the energy of an entire universe, it might have created an incredible simulation. Getting this right in such a scenario is a truly complicated matter. Exploring the depths of cosmology and the origins of our universe leads us into a domain of great mystery and ongoing scientific inquiry. The new pictures acquired by the James Webb Space Telescope have reignited conversations about the true nature of our world, challenging established theories and prompting researchers to reconsider fundamental aspects of cosmological understanding. At the core of this inquiry lies the theory of how things began, a foundation of modern cosmology. According to this hypothesis, around 13.8 billion years ago, the universe emerged from an exceptionally dense and hot state, rapidly expanding, resulting in space-time and matter as we understand it today. This magnificent event was not just an explosion within prior space, but may have included the very beginning of space itself. The concept of a phenomenon where gravitational forces are so intense that space-time becomes limitless supports our understanding of this early stage of the universe. However, the discovery of early systems by the James Webb Telescope challenges assumptions about how quickly systems formed in the universe's infancy. These systems, identified within a few hundred million years of the Big Bang, appear remarkably developed and large in contrast to assumptions based on current cosmological models. One of the inevitable issues raised by these discoveries is the concept of inflation. As proposed by the dominant hypothesis, inflation occurred within fractions of a second after the Big Bang, causing the universe to expand rapidly. Furthermore, this fast expansion would explain the uniformity of the vast microwave background radiation observed across the universe today. However, the new discoveries suggest complexities in the early development of the universe that may require amendments to inflationary models. The formation of galaxies like those seen by the Webb telescope forces cosmologists to rethink the conditions and processes governing the universe's early evolution. These enormous systems, now pivotal in size and mass, suggest a matter density that exceeds previous estimates. The mystery continues as researchers ponder how such vast structures could have formed and evolved in such a relatively short period of time. Moreover, the discovery of these early galaxies raises fascinating questions about the nature of dark matter and dark energy, two elusive components that make up most of the universe's mass and energy content. While dark matter is understood to provide the gravitational foundation for galaxy formation, the distribution and properties of dark matter in the early universe remain uncertain. In line with these astrophysical mysteries, theoretical physicists are exploring alternative cosmological models that challenge the standard Big Bang view. Some hypotheses suggest that our universe is just one among many in a vast multiverse, each with its own distinct physical laws and constants. These ideas, arising from advancements in string theory and quantum cosmology, propose a more complex and interconnected universe than previously imagined. One idea gaining momentum is the concept of eternal inflation, where universes continuously emerge from a larger, expanding space. This theory suggests that our universe might be just one bubble among countless others, each with its own unique properties. The challenge lies in finding observational evidence to support such speculative ideas, as they stretch the limits of empirical validation. Another provocative hypothesis is that our universe exists within a simulated reality, much like a computer-generated game. This idea draws parallels with developments in artificial intelligence and computational science, where simulations can replicate complex systems, possibly providing insights into the fundamental nature of reality. Regardless of the ultimate outcome, these discoveries prompt a shift in the way we understand the cosmos. The James Webb Space Telescope's findings indicate that much about the universe's early history is still shrouded in mystery, challenging scientists to revise long-held assumptions and explore new theoretical frameworks. With all these concepts being proposed, one question is paramount. As the universe continues to expand and evolve, will we ever truly understand its origin, or will the mysteries of the cosmos remain a tantalizing puzzle, with each new discovery raising as many questions as it answers? The journey toward comprehending the universe's true nature has only just begun, and the implications for cosmology and physics are profound as scientists continue to analyze the vast quantities of data gathered by the James Webb Space Telescope. New theories and questions arise, pushing the boundaries of our understanding of the cosmos. These groundbreaking images reveal not only early galaxies and their surprising characteristics, but also provide insight into the complex mechanisms of star formation, galaxy evolution, and the fundamental nature of space itself. The discoveries made by the telescope challenge existing models of how the universe came to be and evolve, suggesting that the early universe may have been far more intricate than previously thought. One particularly intriguing aspect of these findings is the potential role of dark matter and dark energy, two phenomena that are essential to the structure of the universe but remain largely mysterious. Dark matter is believed to account for a significant portion of the universe's mass, and it plays a crucial role in the formation of galaxies. However, its exact properties and distribution in the early universe are still not well understood. The images from the Webb telescope, which include distant galaxies formed only a few hundred million years after the Big Bang, suggest that dark matter may have behaved differently in the early universe than it does today. This raises the question of how dark matter influences the growth of galaxies over time, and whether it might have played a more prominent role in the formation of early, massive systems than previously assumed. Dark energy, on the other hand, is thought to be responsible for the accelerated expansion of the universe. As the universe continues to stretch outward, dark energy drives this expansion, but its nature remains a profound mystery. The discovery of galaxies so massive and developed in the early universe challenges our understanding of cosmic expansion, suggesting that perhaps the relationship between dark energy and the growth of structures in the universe is more complex than the current models allow. Could dark energy have behaved differently during the early stages of the universe's existence? This is one of the many unresolved questions that continue to puzzle scientists. Another major aspect of these discoveries involves the study of cosmic inflation. The prevailing theory of inflation holds that in the first few moments after the Big Bang, the universe expanded at an exponentially rapid rate, smoothing out any irregularities in the distribution of matter and energy. This theory helps explain the uniformity of the cosmic microwave background radiation and why the universe appears to be homogeneous on large scales. However, the Webb telescope's observations of early galaxies raise new questions about the timeline of cosmic inflation and the formation of the universe's first structures. Were these structures truly formed so quickly after the Big Bang? Or was there some other process at play that led to their rapid development? The answers to these questions could fundamentally alter our understanding of the early universe and its evolution. In the midst of these scientific revolutions, some researchers argue that our current models may be too limited to explain the full complexity of the cosmos. They propose that the observable universe may be just a tiny fraction of a larger, more intricate structure that stretches far beyond what we can see or measure. This idea aligns with theories such as the multiverse, where multiple universes coexist, each with its own physical laws and properties. Some even speculate that these universes could be interacting with one another in ways we are only beginning to comprehend. These speculative ideas raise new avenues for exploration but also highlight the limitations of our current understanding. As scientists continue to analyze the data provided by the James Webb Space Telescope, the mysteries of the universe remain ever-present. Each new discovery brings us closer to understanding the origins of the cosmos, but it also introduces new questions that challenge our most cherished theories. The road ahead is full of uncertainty, but it is through these challenges and breakthroughs that we gain a deeper appreciation of the complexity of the universe. The journey to uncover the true nature of reality is only just beginning, and with each step forward, we come closer to answering some of the most profound questions of existence.